We are in our almost end of the unit module. This is module number 10. And the first thing I want to do is just make sure you had a look at the two chemistry demos that I did. The first one was the Diet Coke and Mentos experiment. And so I found these cute little tiny bottles of Diet Coke. I didn't want to waste too much when I was at the grocery store. And so what I did was I took these bottles and I put them at 3 different temperatures. So we used room temperature, so 21 degrees Celsius. I popped one in the fridge, so it was probably about 11 or 12 degrees Celsius. And for the third temperature, that was the one obviously the rate went the fastest. That one was 45 degrees Celsius, and I just popped this into like a hot water bath and warmed it up. So when we took the lid off, it clearly was the warmest one. All right, how does it work? Well, the Mentos provide a surface area for the carbon dioxide to go from aqueous form all the way into gaseous form. So it's just basically dissolved CO2 that's in here, right? And under pressure, the carbon dioxide stays in, and that's what fizzes in the pop, obviously. With the Mentos, they've actually been able to figure out that the Mentos provides a surface that's really rough, and so it has these little divots in the surface of the Mentos at the microscopic level, and they provide a surface area for the carbon dioxide to attach to and then come out of the solution at a faster rate. Okay, so that was our first demo, and that had to do with module number 9 from last week. And for this module number 10, you hopefully already had to watch the surface area affecting reaction rate. And so for this experiment, what did we do? We took the Alka-Seltzer tablets, and I'll explain this a little bit in a couple of minutes, but our Alka-Seltzer tablets we put into little film canisters with some water, and then the carbon dioxide that got formed would be trapped in here, and then obviously it pops off. And so we took the Alka-Seltzer tablet, I'll just show you what it looks like here. It's a white solid substance, and we took this little tablet, it's really a chalky feel to it, and we broke it in half, and one half went into the film canister hole, so large surface, a large tablet, small surface area, and then the other half of the tablet we crushed it up into powder, and then that was representative of an increased surface area. And what were we comparing? We were comparing the rate for the reaction. Okay, so that was our surface area experiment, and how does that affect the reaction rate? So as you can see on your notes, this is the last little bit right here. If we were to explain what's happening at the molecular level, the first thing you want to think about though is the fact that the surface area is only going to be affecting the rate of a reaction if you're looking at 2 of the reactants that are heterogeneous. Okay, so if you're looking at something that's got a solid versus a liquid, then you're reacting the 2 together. You have a heterogeneous reaction. That's a term that maybe we haven't really talked about before. And when you have 2 different phases or 2 different states of matter, well then you actually can compare surface area and see how the surface area will be affected. Because if you think about it, if you have 2 liquids together, that you can't change the surface area if you have 2 substances that are the same state, right? So you don't, right? You need to be able to have 2 different ones, so heterogeneous. Okay, and what do you see? What is in Alka-Seltzer? Well, that's the components listed down below. And then, of course, what you're going to do is be explaining at the molecular level. So when you're looking for key terms, when you're explaining something just like you did for question number 7, from the clock reaction lab, you want to talk about the fact that 1, if you're increasing the surface area, you have more reactant particles. Next point, if you have more reactant particles, then they're going to hopefully collide with a greater chance that they're going to have the correct collision geometry. All right. Also, the third point then is that they need to collide with energy that's greater than or equal to the energy of activation. And when all of those factors come into play, then you're going to have an increased rate of reaction. Okay, so this little paragraph right here is really the summary that we want to be able to take away from this lesson. What happens at the molecular level? Okay, getting into what are the components of the Alka-Seltzer tablet. So again, you would take Alka-Seltzer if you have a stomach ache or a headache. Maybe you're feeling like you have some acid reflux there. You want to be able to neutralize that reaction. So you've got sodium bicarbonate, you have citric acid, and acetylsalicylic acid. That's the ASA that relieves the headache. What happens is you end up with reaction number 1. And you can see right there that with that sodium bicarbonate and your salt and the citric acid, you end up with carbon dioxide bubbles. And so if I take my glass filled with just water and I add my Alka-Seltzer tablet to it, you immediately see all the carbon dioxide bubbles that come up and out. And that is what was happening inside of the little film canister. So imagine that happening in the film canister. As soon as you pop the lid on that, it's going to create a tremendous amount of pressure and it'll pop the lid right off. And in fact, it works best if you add it with a controlled amount of water. Put the lid on after you put your Alka-Seltzer in. Take your film canister, turn it upside down. Can you see that little picture down here below? All right. Put your film canister upside down and it'll completely pop off. And if we were in the chem lab, it would completely hit the ceiling. All right, it would pop off with that much pressure. Provide a bit of a mess as well. So I got a chance to do that experiment outside. Now, if you're looking at just explaining with the variables for this experiment, what were they? Well, our independent variable, that's the I variable, your testing variable. We wanted to see how the surface area affects the dependent variable, which in this case was the reaction rate, specifically the time for the reaction to take place, and then we'd be able to calculate a rate for that. So perhaps carbon dioxide forming over a particular period of time, we'd get a rate value. And when you've got your independent, dependent variable, and some control variables, you have a controlled experiment. We used the same type of container, and we also used the same volume of water. And on my little film canister here, where's the line? I marked it with a Sharpie, so every time James filled it up, he filled it with the exact same volume of water for me. Okay, and then we just summarize it. So what did we get? Well, I didn't show you I did write in the video what time it took for the reaction to take place. When we had our tablet that was intact and whole, the time it took was 20 seconds. So that's relatively slow. We have a low surface area for our intact tablet. And when we broke it in the other half of the tablet and broke it into tiny little pieces, then we have a high surface area. Our time it took for reaction is going to be less, and it was actually 8 seconds. And so our rate would be faster. Okay, and that's the observations you would take and make a conclusion based on how does the surface area affect the rate of a chemical reaction. Next part of this lesson is to look at a catalyst. And this is something that's going to come up in biology, chemistry, physics. You'll talk about catalysts, so it's important that you understand what the definition is of a catalyst. And I'll fill this part in, I'll fill all this in, and then I'll post the notes so you can see. Just talks about hydrogen peroxide, and if we had a chance to do it in the lab, we would add a catalyst, potassium iodide, to it, and it's going to just basically produce water, and that's it in the end, right? So what does a catalyst do? It is a substance that increases the rate of a reaction by decreasing the energy of activation. Remember, a catalyst isn't shown on the reactant side or the product side. It's always shown over the arrow in a chemical reaction, and that's the indicator that a catalyst was used for that reaction. Okay, you can think if you've taken bio already, you talk about hundreds, thousands of catalysts, right? So many catalysts when you're doing cellular respiration, when you're talking about photosynthesis, and all of those chemical reactions mostly can't take place without the effect of a catalyst, right? If you were to take a potential energy diagram, okay, so that's what I've got right here. You can do your own, you can follow mine, but basically you want to show and label a potential energy diagram for an endothermic reaction. So you can see here it's endothermic, right? So your reactants have less energy than your products. So if you were to take the difference between them, you'd have a positive value, okay? And that's the potential energy difference. And at the very top of the diagram, you can see right here, with a catalyst and without a catalyst, you see the effect of decreasing the energy of activation. Okay, and then there's a few more things to read on the rest of this page about catalysts, and that's it. So that's our last module of learning for the unit, which I can't believe we're already done. We're going to spend the rest of the week working on some of the calculations that are on the next couple of pages, including the sample multiple choice test, okay? So I hope you enjoyed the videos. That was most fun for me to do, and we'll talk to you later this week.